In this video, we're going to look at writing exponential equations from a graph. So here we have a graph of a function, and I'm going to show you how to write an exponential equation for that function. I'm going to show you a couple of different ways of doing that. So the first thing I notice about this graph is that we have an asymptote at y equals -3. That's going to be really important because any parent exponential function would theoretically go through the point 0, 1 and would have some sort of an asymptote at y equals 0, right? So we would expect to have some sort of exponential curve and get really close to 0, but never actually get there. So that's where our asymptote should be. But because it's at y equals -3, the only way we can move this graph down is with a vertical transformation. And so when we go to write this, actually let's keep that. When we go to write this equation of our actual curve, I need to keep this in mind. And so I'm going to use the form y equals a times b to the x plus k. And k is going to represent our vertical transformation because a times b to the x, like that's still going to create an asymptote. As we raise things to really negative powers, this is going to approach 0, but k is going to be still there afterwards. So this part approaches 0. 0 plus k is just k. So as this part approaches 0, our curve is going to approach k. So where we see this asymptote here, as a times b to the x goes to 0, rather than approaching 0, our function's actually going to approach this k value. So all we want to start with is good old-fashioned k. And k is kind of attention-seeking like that. So it wants to be started with first. So we're going to go, okay, k, we'll start with you. So we'll say y equals a times b to the x minus 3. To have a complete function here, all I'm going to need is this a and this b. Right? Y is just y, x is just x, and we'll be happy. And luckily, we actually have 2 points that we can use. We have 6, 5, an x and a y point, and we have 3, -2, another x and y. And so by setting up a system of equations, we're going to be able to actually solve for the 2 unknown variables because we'll be able to set up 2 equations. So I can set up 5 is equal to a times b to the 6th minus 3. I can also set up -2 is equal a times b to the 3rd minus 3. So method number 1 here is I can do elimination. I can look to eliminate one of the variables so that I can solve for the other. And it looks like a really doesn't belong, right? No. But it's all by itself and it's ready to be eliminated. So if I were to just divide these equations, I might expect the a's to cancel and I would just get left with b. But the problem is I can't divide them yet and cancel because I'm dividing 2 terms by another 2 terms. And so that's not actually going to cancel in the way I want. So it's really important that before I go and divide anything, I'm going to add 3 to both sides and isolate the a times b to whatever power. So by doing this, I'm going to get new equations. 8 equals a times b to the 6th, and 1 equals a times b cubed. Now when I go to divide this, it's okay because all of this is multiplication. And so when I do division, a times b to the 6th divided by a times b cubed, right? Now these cancel because there's no other extra terms that I have to worry about that interfere. So without having those k's, this actually works. So I get a divided by a is just 1. They cancel. 8 divided by 1 is 8. And b to the 6th divided by b cubed, well, that just gives us b to the 3rd. So 8 is equal to b cubed. And so if I take the cube root of both sides, I get b is equal to 2. Now I can pick either equation and substitute b back in to figure out what that would make a. So I'm going to pick this first equation. I'm going to say 5 is equal to a times, now I've got a b value, 2 to the power of 6 minus 3. So I can make this 8 equals a times 2 to the 6th. 8 is equal to 2 to the 6 is 64. 8 divided by 64 is equal to a, and a is going to be equal to 1 over 8. So my final equation is y is equal to 1/8 times 2x minus 3. If we take that, bring it up, compare it to our graph, you can see that this seems to make some sort of sense. Get this out of the way. Okay. And we definitely have this asymptote of y equals -3, 1/8, and 2 to the x. So it looks good. I'm going to show you another method, though. If we didn't want to use elimination, I could also set up the same system of equations, but instead I could use substitution. So just like with linear systems, we usually can use elimination or substitution, it's going to work with our exponential systems as well. So take a look at that. We can say, using our points, we can say 5 is equal to a times b to the 6th minus 3. We can say -2 equals a times b to the 3rd minus 3. And with substitution, remember that our goal is to isolate one variable in terms of the other. And looking at this, I think I want to isolate a in my second equation. And once I do it out, maybe you'll see why I choose this. So I'll add 3 to both sides of this equation. I'll get 1 equals a times b cubed, and I'll divide by b cubed on both sides. And I'll get a has to be equal to 1 over b to the 3rd power. Great, so I've isolated for a, and then now if I take my other equation, I can substitute in for a 1 over b cubed. So I'm going to say 5 equals 1 over b cubed times b to the 6th, all minus 3. And b to the 6 is the same as b to the 6 over 1, and so this whole fraction is multiplied by this fraction, and we end up just with b to the 6 over b cubed equals 5, and we still have to subtract 3. Okay. Now, the reason I happen to choose this equation here to isolate is because I kind of knew, I've had some practice, that once this was all said and done, we would end up with something in the denominator. And I wanted my b cubed to be in the denominator because b to the 6 divided by b cubed is b cubed. And I prefer to keep my exponents positive if I could help it. The other thing that might have happened is we would have gotten something where we would end up with b cubed over b to the 6. That would work just as well, but then we'd get b to the -3. And I just like to keep things positive, you know? Got to stay on the positive side if we can. So this is -3, and this is 5. Then we go and solve this. We get 8 equals b cubed, cube root both sides, and we get b is equal to 2. You'll recall that that was what we got when we used elimination. And then I can go ahead and I can substitute this value of b back in for b. So that gives me 5 equals a times 2 to the 6th minus 3. Add 3 to both sides, giving us 8 equals a times 2 to the 6th. 2 to the 6th we said was 64, so 8 equals 64a. 8 over 64. Looks awfully familiar, doesn't it? And a equals 1/8. So when it's all said and done, we'll end up with y equals 1/8 times 2 to the x minus 3. And so regardless of whether we use substitution or elimination, we're going to get the same answer. And we got a green circle to come along with us too. Have fun. Okay. Do you remember the last way to get the solution to a system of equations? By graphing. So that's kind of trickier. But you could try to solve this through graphing. So if you wanted to graph this on Desmos, our third way to solve a system is by graphing, right? And we have these two equations that we set up from our system. Essentially, we had 8 equals, or actually, let's just do the whole thing. 5 equals a times b to the 6 minus 3. We also have, what did we have? -2 equals a times b to the 3rd minus 3. So we have this system of equations. Now, if you want to put this into some software, Desmos is usually going to be your friend to do that. But Desmos doesn't really like a and b. It does everything in terms of x and y. So if I want to solve this, I could just rewrite this as 5 equals x times y to the 6 minus 3. And I could also do negative 2 equals x times y to the 3rd minus 3. So if we plug those two equations into Desmos, let me see if I can find and or remember this. Desmos. Got a lot of apps here. Where's the Desmos? Desmos. Aha. Okay. So if I want to solve this using Desmos, if my memory serves, we had 5 equals x times y to the power of 6 minus 3. We get this beautiful funky curve here, but we don't care because we just want to know where that intersects the other equation, negative 2 equals x times y to the 3rd power. And so we get another kind of funky, beautiful little curve. But what's really noticeable is that Desmos shows us our point of intersection. And if we click on that, we see that it is at 1/2. Hello. Comma, negative 1.5874. So that doesn't exactly look right because I forgot the minus 3. Now with the minus 3, we get here and we get 0.125, aka 1/8, and we get 2. So that tells us that, can I write on this? No, but still, what a video, right? We get 0.125, aka 1/8, and we get 2. So if I go back and reuse this as the equation in this, I can say, oh, look, my graph told me x was 0.125 and y was 2. And so now I've got my function y equals all this. And 0.125 is the same as 1/8. Okay, so thanks for sticking around. Now I actually showed you, you got an extra free one, 50% off. You got graphing, we did a substitution method, and we did an elimination method. There's plenty of different ways that we can write the equation of this curve. Hope you enjoyed the video. Thanks for watching.